This is everybody's favorite liquid, but don't drink it. That's because it's not water, which is boring, and it's also not alcohol. Rather, it's an incredibly powerful liquid made by mixing alcohol and vinegar, which at first sounds disgusting, but will smell like a pineapple on steroids if you esterify them via reflux for 3 hours, distilling the portion under 100°C, washing with bicarbonate and brine, then redistilling. That's right, it's the most loved solvent, ethyl acetate, and today I'll be making it from scratch. It's crucial to your life, and by the end you'll agree that it's the GOAT. Now lock in, because you're about to witness one of the best feats of chemistry on the Carbon-12 channel yet. And the final purity was so shocking, I'd never seen anything like it, even if a few things didn't go according to plan. So let's hop right in. Step 1. Grab the materials. Now we're already getting into one reason why it's the GOAT. It's the easiest to make. Ethyl acetate is made through a rather simple reaction, as it only requires 3 chemicals. Surprisingly, it is still quite a challenge to achieve a decent yield due to the reaction being an equilibrium one. The 3 chemicals we're going to need are some glacial acetic acid, anhydrous ethanol, and some concentrated sulfuric acid. But before I open up these bottles, seriously I have to tell you that opening a bottle of acetic acid will make your nose suffer. Like, it is extremely unpleasant to go near this thing, so I did it in a fume hood. It's like nuclear salad dressing. But surprisingly, ethyl acetate smells really good, and just a sneak peek of the smell test later, it's like a sweet, genetically modified Axe body sprayed fruity pineapple on steroids. A second reason why it's the best, although you still shouldn't huff it. And yes, I will get to making some genuine glacial acetic acid in a future video as round 2, because I failed quite horribly the first time. You guys did give a ton of strategies though, and round 2 of the fight will use every single one of these methods of attack. Yeah, we win in this fight, man. I ain't losing to some puny carboxylic acid. Step 2. Setting up the reaction. Without waiting any longer, because patience left the chat, I got a retort stand, and on top, I put it on a 3-necked 1-liter round bottle flask. This will be our reaction vessel. Thus, into this I then carefully transferred all of my 150 ml of acetic acid through the right neck. From the stand, to the ring, to the drip, to the flask, my setup was looking pretty complete. I was quite careful and made sure to not spill any in the thick of it, as everybody knows this stuff is quite expensive. I then poured in the 150 ml of ethanol as well on the left, which I made previously in a massive multi-liter extraction operation. Finally, I know you've all been waiting for this, but 20 ml of concentrated sulfuric acid was slowly poured in drop by drop. I like my H2SO4 drippy, bruh. Okay, seriously though, it's important to do this step slowly as it can get quite hot, and if it does start to boil, you could lose a lot of your reagents and your reaction won't work as well. Mine actually got quite hot to touch, so I kept on swirling it around and added it in bit by bit. Just a quick tip, it may have actually been better to put this into an ice bath. This part did erode my patience though, and when it was finally finished, I can move on to actually starting the reaction. Step 3. Glassware. Behold, one of my most unique pieces of glassware. That's right, it's something called a Soxhlet extractor, named after Franz Ritter von Soxhlet, and today we're going to be using it for a really cool and niche purpose. But before that, we're going to need to set up our reaction vessel, and this will require a hot water bath as I unfortunately still don't have a temperature monitoring heating mantle. I will get one though sometime soon, I promise. The hot water bath will be crucial for maintaining a moderate temperature under about 100°C. Then we can get back to our Soxhlet extractor I was talking about earlier. This is a method commonly credited to the OG one and only Nerd Rage, and it'll be essential for this esterification. Basically, I first need to put in a piece of paper at the bottom, and then pour in some molecular sieves to fill it up. If you're wondering why paper needs to be put in place, it's so that the sieves won't clog up the tubes, because if they get in there, you're gonna have a bad day. Now the activation energy for me getting a smaller container is apparently very high, so to transfer in the sieves from this massive 3A sieves container, I legit just got a powder funnel and thought I could magically make them all pass through without spilling. Result? Well, turns out I don't have sieve bending abilities, so now they're all over my fume hood. Seriously, I've said this before and I'm gonna say it again. I hate molecular sieves. Other than the satisfying ASMR they make. Anyways, I also switched to paper for like a little ball at the bottom as I think it works better. And now with a more suitable pouring container, I transferred in all of the sieves. I think I also filled it up maybe a bit too much, and since I don't want any to go into the pressure equalizing tube, I poured out a bit. Finally, on top of this, I can put on my nice reflux condenser. This one goes with the Soxhlet and has a really beautiful bulb structure, just like the ones Walter had. And yes, holy smokes is this setup tall. If there was a build limit like when me and the bros were gaming back then on Minecraft, this would have definitely broken the law. This is even taller than a fractional distillation, and definitely the most massive setup I've made on this channel yet. Due to its size, it was also feeling kind of wobbly, so I made sure to secure it one more time higher up with another clamp. Now everything was looking quite ready. But wait, one thing still isn't. That's right, I haven't filled up my condenser with water yet. So I grabbed my pump and put some ice cold water in it. Now, I can actually say that we can start the reflux. Step 4. Refluxing. Now turning up the heat and stirring, the reflux can finally be started after the annoying amount of time I spent getting it ready. This reflux is done at around 80 C for the reaction to happen at a decent rate, as if you don't give the particles energy, they're not going to do much, just like me on an average Monday without my coffee. Maybe I should mass extract caffeine in a future video. Anyways, in order to not lose any of our reagents here as they are quite volatile, the condenser acts to turn the vapors back into a liquid and make sure they drip back down, coming back to the flask. Now you might also be wondering, why the heck do I need such a monstrosity of a setup for this simple reflux? And that's a fair point. In the past, all I used was a Liebig condenser, but this reaction is different. I know it may seem like all of this might be a lot of work, but trust me, in the end it's going to be all worth it and the final result is crazy. But do you know what else is crazy? Being able to learn interactive and advanced concepts anytime, anywhere, all on a 6-inch screen, which brings us to the proud sponsor of this video, Brilliant. Brilliant is one of my favorite platforms to learn math and science, online or mobile, featuring a wide range of topics from circuits, which I'm a newbie in, to calculus and derivatives. But the best part is how interactive it is. Not only does it immerse you into the lesson to play with switches and functions, it also makes you a better thinker through this process, a method proven to be 6 times more effective than watching lecture videos. It equally allows you to attain serious goals, keeping you on track one day at a time, learning a little each day. So what are you waiting for? To learn for free on Brilliant, go to brilliant.org/carbon12, scan the QR code on screen, or click on the link in the description. Brilliant has also given Carbon 12 viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. So thank you to Brilliant for keeping the lights in my lab on. And back to, where was I? Oh right, the setup. You see, the reaction we're doing here is something known as a Fischer Esterification, which is a reaction where a carboxylic acid is reacted with an alcohol to form our ester and water. Now everything might seem like it's okay, this makes that, it all adds up. It's all sunshine and rainbows. But wait, the real world is much more annoying and the reaction in fact does not go to completion, which means not 100% of the reactants are converted into products. Instead, this reaction is an equilibrium reaction, and according to Wikipedia, only about 65% of the reactants turn into products. So how do we push this reaction further and obtain more yield? We need to leverage Le Chatelier's principle here, which can be done either by using a large excess of a reagent to push the reaction, or by constantly removing a product. It is exceptionally fascinating, and I just realized I never really explained how this works, and you might in fact not know why nature does this, but it's in fact just to relieve stress. Think of it in terms of economics. Imagine you have a factory that converts raw materials into products. If products are constantly being bought and taken away, aka demand is high, the factory will scale up production to satisfy it, or pushing the reaction to the right. If they have a large excess of raw materials or supply, it will also ramp up productivity to make more products, again shifting towards the right. In fact, here we are doing both of these. We have an excess of acetic acid, and we are also constantly taking away one of the products, specifically the water. Now stay with me, because this is pretty cool. The only thing that's different about this from a normal reflux is this part in the middle, and although it looks complicated, all it does is pass the vapors through the sieves before returning it back. Here you can see our setup and the molecular sieves. In the boiling flask, we have acetic acid, ethyl acetate, ethanol, and water. Now since the reflux will max out at around 77 C, which is the boiling point of the lowest boiling substance, ethyl acetate will boil and be condensed. A lot of ethanol will come over too, as it boils just 1 degree above that. Along with this, a significant amount of water will be in the vapor as well because of the increased vapor pressure, but also due to ethanol co-distilling it and dragging it along via hydrogen bonding. So all 3 of these substances will flow back down. But how do we selectively remove the water? That's where the sieves come in, specifically 3A molecular sieves. These things are zeolites, aluminosilicate cages that can absorb things of specific size depending on their pore diameter, and the 3A here stands for 3 angstroms. An angstrom is roughly the diameter of a chlorine atom, and so small molecules less than 3 angstroms like H2O can pass through, but ethyl acetate and ethanol are way too chunky to be absorbed. Thus, these sieves are selectively removing water, and the returning solution should be just ethanol and ethyl acetate. Isn't this quite cool? But what's even cooler is what's really happening on the molecular level, as so far, we have only described the Fischer Esterification in this simple equation, but like previously, the real world is much more complicated and reactions actually happen through a mechanism, or a series of steps that is followed. Without seeing this, you might not understand why an acid is used, and how it catalyzes the reaction, but it's indeed very fascinating. As you already know, in our round bottom flask, we have our reagents, ethanol, acetic acid, and sulfuric acid. With sulfuric acid though, it will completely dissociate as it's really strong, forming hydronium ions in solution by transferring a proton to water. Now what's going to happen is that the hydronium can do a proton transfer to the carbonyl oxygen from acetic acid, protonating it and giving oxygen a positive formal charge. Of course, this makes the oxygen really angry as it hates this positivity because it's electron thirsty, and thus an ethanol molecule will come over to help his friend out, connecting itself onto the carbon center and pushing an electron pair onto the oxygen. However, the ethanol oxygen now has a positive charge. The problem isn't solved, just at a different place, so a game of hot potatoes kind of going on here. From here, an intermolecular proton transfer can happen, where one of the alcohols will grab that hydrogen, relieving stress there but creating another problem here, an oxonium ion. On the other hand, another possible mechanism is that a water molecule and a hydronium ion can come in, one of them donating a proton and the other taking one, forming again an oxonium ion. Notice how we obtain the same intermediate both ways. Conveniently, the oxonium ion is also a great leaving group, so with the push of an electron pair, it falls off, forming water. Finally, our positive charge is on the carbonyl oxygen again, and to get rid of it, it can just deprotonate itself, reforming our hydronium. You see, it never gets used, just the catalyst, which is why the sulfuric acid is so indispensable here. You can see all of our products form as well, just like in the equation. In fact, many reactions use an acid catalyst, as it often introduces a positive charge, which is unstable, and instability is what gets a reaction going. Step 5. Distillation. Now after refluxing this thing for 3 to 4 hours, yeah, I know it's a long time, but you really want to cook it low and slow so you get that nice medium rare interior. Anyways, we can finally take it apart. To my surprise though, apparently many YouTubers only reflux it for around 30 minutes, which is actually quite strange. Does anyone know why? Do they like their esters blue rare or something? Anyways, after the reflux, you can see that there is no specific layer separation. This is due to ethyl acetate's miscibility with water. To collect most of it though, we can set up a distillation. And you shouldn't cut corners with a short path due to its volatility. Here you can see me painstakingly putting it all together. Now for this distillation, in order to collect as much of our ethyl acetate as possible while reducing the amount of water, all we have to do is collect a portion under around 100 C, which should be mostly ethyl acetate, water, and maybe some residual ethanol. At around 100 C, mostly water starts coming over, which is when it should be stopped. After finishing the setup, I cranked up the heat as well as the stirring, and let's get this party started. Now this distillation is a really fast one, as just like when distilling any volatile solvents, it drips over really quickly. It's also very satisfying to watch, to be honest. Slowly but surely, the temperature creeps up towards 100 C. I thought the 250ml round bottom flask might have not been enough volume, but it turned out to be alright, as the distillation was about to end. Also, can someone tell me in the comments what this piece of glassware is actually called? It's kinda cursed. Like, is it called a flat bottom round bottom flask? That's so contradictory. At least it increases the surface area though, so it's better for a hot plate. Step 6. Washing. Now when the distillation finally hit around 95 C, I decided to remove our receiving flask and stopper it, which should now be mostly ethyl acetate. Just to double check it though, I gave it a whiff, because we're definitely in the 1800s, right? I would not recommend this with other solvents though, but as expected, it smelled exactly like tropical fruits. Now a decent amount of water and maybe some ethanol is still here, And if you're wondering why it doesn't form two layers, it's because the two are actually slightly miscible. Thus, it might be quite difficult to remove it unless we do some washing steps. Specifically, we need to wash it with an aqueous saturated sodium bicarbonate solution and then a saturated sodium chloride one. I know, what a mouthful. Before we do that though, I first got a retort stand and placed onto it a 250ml separatory funnel, as unfortunately that's the only size I have. Now I brought the funnel to the party because last time, things got messy, literally. Yeah, I learned my lesson, alright guys. I then poured in all of our crude ethyl acetate, and you can see it basically fills up the entire thing. It would be very difficult to do washings when it's this full, so I had to unfortunately pour out a bit and do it in 2 batches. I mean, what did you guys expect? Me to have a sus 24-liter separatory funnel which is definitely not being used for the mass synthesis of blue crystal. Anyways, literally underneath this, I got a beaker with a decent amount of salt in it. And if you're asking, yes, it was absolutely not from my kitchen. I then started pouring in water to dissolve it. I also tried stirring it around, but it seemed like it wasn't dissolving that well. Strange. Maybe there's some impurities in my salt? It said ACS grade though, over 99% purity. Okay, sorry Sigma, this is actually a ripoff. Alright, now to the right of this, I got another beaker with baking soda in it and made an aqueous solution again. Cranking up the heat on the hot plate, I hoped that this would make the dissolving step easier. After tirelessly stirring these around for like 15 minutes, it didn't seem like any more salt was going to dissolve, so I just thought it was good enough, like what Carbon always says. Then, into our separatory funnel, I first slowly poured in our sodium bicarbonate solution. The reason we have to do this is to first neutralize any remaining acid, and as you can see, a good amount of bubbling takes place. This can be seen through this bicarbonate neutralization equation, with carbon dioxide formed. However, since the two now separate into layers, the aqueous layer sitting on the bottom, the neutralization won't be very effective due to the low contact area. In order to fully neutralize it though, I'm going to have to shake it around, and this is the riskiest part because a lot of gas is formed. In the bicarbonate neutralization, carbon dioxide is released in actually a pretty good amount, so you're really going to have to constantly vent this very well. As you can see here, I didn't, so the pressure built up a bit too much and the stopper kind of flew off, spraying some of the liquid everywhere and making a huge mess. And trust me, it was not fun to clean up. This may have also ruined my yield quite a bit, by the way. Anyways, it is what it is, and you should wash the bicarbonate solution until no more fizzing occurs, draining the bottom aqueous layer each time. And it definitely tested my patience. To be honest, washings are always longer than you expect them to be. This one took me like an hour, which was actually kind of better than my previous one, which took a solid 3 hours due to some unbearably annoying surfactants which made separation difficult. The whole time it was giving vibes of, I've played these games before. Okay guys, season 3 was horrible though. Alright, now after the neutralization we can start washing with our brine, or saturated sodium chloride, by pouring it in portions. This is a laboratory technique known as salting out. Anyways, there are some beautiful aspects of this tedious process though, like seeing in close up how the layer separates by forming these small globules that slowly agglomerate together. Isn't this mesmerizing? Here you can see me pouring in the salt solution, and if you are watching closely, you may be asking, why was the water and ethyl acetate miscible right after the distillation, but as I started washing with bicarbonate and salt it formed 2 distinct layers? This is an excellent question, and it exactly touches on how these washings work, which I find is actually rarely explained. You see, water is highly polar with a net dipole moment, and forms strong hydrogen bonds with itself. Ethyl acetate, on the other hand, is only moderately polar. It can't hydrogen bond with itself because there's no hydrogen attached to a highly electronegative atom, but it can act as a hydrogen bond acceptor. The lone pairs on the oxygen in the ester can interact attractively with the partial positive hydrogen atoms in water. That means water and ethyl acetate can mix, partially. After distillation, they form a single homogeneous layer because their intermolecular forces, while not exactly identical, are compatible enough to stay mixed at the concentrations you get from distillation, especially when warm. But when I start washing with brine, bicarbonate, or any ionic aqueous solution, I'm adding a ton of ions into the water layer, like Na+ and Cl-. These ions are very strongly hydrated. They pull water molecules around them into tight hydration shells through ion-dipole interactions. This disrupts the hydrogen bonding network between water and ethyl acetate, leading to the water ditching them for the ions. This is because the ion-dipole interactions are stronger than these partial de facto hydrogen bonds, which are honestly kind of a mess. They're stronger because more energy is released, and for you nerds out there, this can be seen through Coulomb's law. The larger the magnitudes of electrostatic charge, the larger the force. Pretty cool, right? Step 7. Drying. Now after those washings, which took like an hour, I can finally take some time to admire my clean ethyl acetate, which is looking pretty nice. However, just like with any organic liquid, there's always going to be some water still in it. Thus, to get rid of that last bit of moisture, it's crucial to use a desiccant to suck it all up. And here I'm going to use calcium chloride, CaCl2. After putting in a good amount, I wasn't completely sure if it was able to remove all the water. According to the internet, a good rule of thumb is to add it in until no more clumping occurs. Oh well, you guessed it. I just added the amount I thought was good. Step 8. Redistilling. Finally, after drying, it's time for one last distillation. This is usually not necessary, but I wanted to do it just to increase my purity a bit more. During the distillation though, I noticed something strange. For most of the distillation, the temperature kind of just stopped at 70 C. I didn't really understand at first why this was the case, until I realized that there's probably still some water in it, and what was boiling at this temperature actually corresponds to the ethyl acetate water azeotrope. Thus, I just let it be and distilled over the azeotrope. After almost all of it came over in the 70 C to 80 C range, the temperature started to creep up towards 100 C, which was when I removed the flask of wet ethyl acetate. Just to show that there was still water in it, you can see that when the temperature reaches 100 C and I continue to let it run, water starts condensing on the glassware and its high surface tension makes it very recognizable. I guess I should have listened and added more desiccant. Now earlier, I talked about how ethyl acetate is crucial to society and even your daily life, because I mean, it is. Ethyl acetate is in your nail polish remover as it's a powerful solvent for dissolving many things, specifically the organic polymers like nitrocellulose used in nail polish. It's also used to industrially decaffeinate coffee because of caffeine solubility in it, but mostly because of its low toxicity compared to other organic solvents. In addition, due to its pleasant aroma, it's also used in candy and perfume, and surprisingly, it's even in wine and contributes to its taste. So next time you sip a glass of wine, you might just be enjoying a tiny bit of ethyl acetate. Step 9. Drying. Now after adding back in some more calcium chloride to dry it, I let it set for a couple of hours to really make sure it was moisture free. When that was done, it was finally time to weigh it to calculate its purity. I mean guys, this is our final ethyl acetate. After all of the days of work, distillations, hours of refluxing and washing, this is what it has amounted to. So let's see the results. So after this whole process, I was left with 86 mils of ethyl acetate, and to calculate its purity, I'm going to compare its density to the theoretical. And the final purity is over 99%. I mean guys, look, I'm not cheating. The measurements are taken precisely at 25 C, the meniscus is exactly at 50 mils, and the mass on the scale reads 44.87. The density is thus 44.87 divided by 50, giving us 0.8974, which is practically on the spot the theoretical at 25 C. Nice. Now I wanted to say that it's technically like 99.9% pure, but there's still a good amount of uncertainty with my garage level labware. Anyways, the yield was a little less, around 50%. I know, this is not amazing, and I think the reason it got this low was due to the minor accident during the washings. After washing it so many times with water though, some of it may have also dissolved into the disposed solution, so be sure to keep that in mind if you do try this out. Step 10. Some cool tests. Now personally, I think ethyl acetate is a pretty exciting solvent, as it has some cool properties other than its fruity smell. For example, it's very flammable, just as flammable as gasoline or acetone, and you can see the nice blue flame it lets off when I light it on fire. What's also pretty cool is that due to its structure, it can also dissolve styrofoam very well, and I mean very well. Like here you can see me pour some ethyl acetate into the glass, and I can put a bunch of styrofoam into it and it just keeps on melting it down. I'm really surprised I can squish handfuls of peanuts all into this small shot glass. That's because styrofoam is actually mostly air, and ethyl acetate breaks the weak van der Waals and pi-pi interactions holding the polymer chains together, causing the foam to collapse. I actually find it quite satisfying, to be honest. At After putting in as much styrofoam as I can, you can see that it turns into a goopy mess. And this is actually quite dangerous as it's both flammable and sticky. Yeah, there's no way I'm getting it off this glassware. Unfortunately, I think I'm going to have to sacrifice this one for boiling chips. At least it was only 50 cents. Anyways guys, thank you so much for sticking till the end. I also want to thank my patrons or supporters for helping me as a high school student, and I will provide behind the scenes, early access, shoutouts, and more. Just a couple of dollars goes a long way in helping this channel to continue providing quality and educational chem content. Anyways, I want to thank you again for watching till the end, and please consider clicking the subscribe button down below. Thank you again for watching till the end, and please consider clicking the subscribe button below.